So let's come back to the medium access control and the cooperative advantage there. So it's a work back from the time I was in University of Ferrara together with my colleagues here. And the idea was, what can we do in multi-hop networks to increase the data rate, right? Because data rate, if you can increase it, this means in the cooperation cluster, somehow you can bring down the price. And the problem was there with IEEE802.11, you had the medium access control in a certain way that you had here 6 devices, and station C wants to send out a packet to D, and therefore it sends out an RDS. CDS will stop all its neighbors, in this case station B, and now station D will answer with a CTS, clear to send, on the ready to send message, and with the CTS also the neighbors, in this case station E, will be stopped to not send within a given network allocation vector. So once this is done, you can exchange it, but with that there's a lot of degradation, right? You have a lot of stations that are going down, not transmitting anymore, whether it's the exposed or the hidden terminal problem, and the question is, can you do something more to use the bandwidth more efficiently? And even if you have 11B or 11A, there are higher data rates, but the efficiency ratio will remain the same. And this is because the medium access control is so bad. In both examples now, we'll talk about this. If you have a multi-hop scenario, we always assume that the closer you are, the better is the data rate, just pass loss in this case. This is given to the data rate aggregation of or adaptation of IEEE802.11a. Now, the problem is that we all sit on the same channel, and that we will do there the RDS CTS exchange in a lower data rate. This will take time. So what we now need is, we could say that we are, instead of using one channel for all of the devices, we take a random approach. We take suddenly different channels when we want to communicate. Problem is, of course, the idea first of all is to reduce the RDS CDS problem, because if not all are sending on the same channel, you're getting this down. But the problem is you get lower connectivity. So if you have n channels and you jump on one of them to communicate, then you can only find 1 over n devices. And then routing over different channels becomes difficult. You can even assume that you have two network interface cards, that at least you can go to a different path, and then they will send you to a different path again. But this becomes complicated. Then we can say all terminals will use the same channel. There's a static approach. That is, of course, the one we had before. It's a little bit inefficient because you will lose only 1 out of the n channels, but then you have full connectivity, right? Random is less problems with RDS CDS, and static is inefficient by design. So what we would like to do is introduce here a new way. It's called dynamic approach with fully connectivity, and we will use all the channels, but not at the same time, but I will show you how it works. So if you have a sender and a receiver, we take our n channels and we take one channel as a signaling channel and the other one as dedicated channels. So what we will do first is to ask the sender will send an RDS over the signaling channel so that the receiver can hear it. All other stations around can also hear it. Then with this RDS CDS, we will announce which of the dedicated channels we see as free at the moment. Then the neighbors knows about it, and they know potentially he will use the channels very soon. If the receiver is issuing a CTS on the channel, he will then say on which of the dedicated channel which were in the offered list will be taken, and he will say this channel please, and all the neighbors of the receiver will now understand that this channel should not be used for a given time. Then the sender will send a probe on the given channel to understand on which data rate they can communicate, and there will be a second CTS on the on the on the signaling channel, because only now the network allocation vector can be set in the right way for this given channel. And the network allocation vector is set, then we send the RDS, and then we are sending it out, confirming it. So also the network allocation vector is set here, over here. And then we send the data over the dedicated channel with a given acknowledgement over the same dedicated channel to transport. So now the signaling where probing and acknowledgement is also a form of signaling, but an in-band signaling over the dedicated channel. All of that has been exposed to one signaling channel. It's a little bit inefficient, lower data rates, but all the devices can listen into that one. And while you are jumping to the dedicated channel, there's a little bit of problem, what you see here. So if you do some transportation, it could be that you are, while you are jumping to the dedicated one and you come back, that you are trying to, you did not listen into the signaling channel as you were busy on your dedicated channel. When you come back, you did not hear about another RDS-CDS exchange, and you might kill another data rate exchange. So it would be nice to have two network interface cards, one given for the signaling channel and one for the dedicated channels. We did then some simulation results. Diego Angelini did it at that time. We looked only at the Mac performance with no real multi-hop at the given point. Very easy. We had a surface, and we just send out data in a given surface area of 30 by 30 meters, and we have these two things, static and dynamic, right? And if you look at the megabit at the time, you see this is a classical approach. Then you have the standard IEEE802.11. You have a static choice, right? Or you have a dynamic choice. So you see already there's a lot of capacity to gain. And the question is now, can we do something to bring down the collisions a little bit more? I told you already a second Ethernet card would be nice. And do we need all the probing packets? There's a little bit of improvement we did. What you see here on the left and the right is some data throughput analysis for one wireless network interface card and two wireless internetwork cards. And you see, especially if you have only a small number of parallel channels, the second wireless internet card helps. If you have enough parallel channels, the likelihood of colliding is not so high, so therefore you don't need it, right? Still giving you more bandwidth, but not that much as, for example, for 2 or 3 or 4 channels. Now, if you take a real multi-hop scenario, now we have 60 wireless terminals, and a sender will choose randomly one of the 60 terminals to send a packet. We take shortest path routing for multi-hop communication. We look at the packet delivery and the transmission delay. And we have now the static choice, the random choice, and the dynamic choice. And here you see the packet delivery over a certain area. The larger the area is, the lower is the connectivity. But what you see nicely is that the dynamic choice is the best. The random is not very good, and the static choice is first like the randomized, and then later with less connectivity is joining the dynamic choice. Not only the packet delivery is important, but also the transmission delay. And there you see it's a logarithmic scale here. The static choice will cause a lot of delay, while the others have very good delay. And the static choice has a little bit larger delay than the random one, but the random is only as good because the ratios were so low. So if it transmits something successfully, then there was not so much traffic. The rest was discarded, and therefore the delay was quite good. But here with the dynamic, you have good throughput, good packet delivery, as well as the latency. Good. A second example for cooperative medium access is looking into the same inefficiency of 802.11. And in communication lecture 1, we have calculated from the students from our task this nice maximal theoretical throughput over the packet size. And you see the larger the packet size is, the better is the throughput. Now, you know that if you have 54 megabit, the throughput of the applications On the higher layer of way lower than that. If you get half of it, you're quite lucky. And this is because of this kind of framing with RDS, CTS, and all this pausing in between. The whole time here is you have to look that the real data transmission is the only efficiency here, and that is decreasing you. So the larger the packet you can do, the better is the efficiency. And that was the idea of IEEE802.11 to have packet aggregation. Instead of sending one packet, just send multiple packets, right? And we are using this packet aggregation for our corporation. So how is this possible? First, let's look into the packet aggregation. You would have a normal RDS-CTS exchange, and then instead of sending one packet, you are sending multiple packets in a row. And this quite one after another, I think with the sieves in between, and then there will be a long collision phase, and then another station will try to get access and send also a lot of packets. So virtually you're increasing your packet here. In a corporation, it is a little bit different. We try to have the same way. We have an RDS-CTS. We are asking to send 4 packets as before, but in this case, the station will only send, the blue station here will only send 2 packets, and then allow the neighbors over the short range and say, you're allowed to send also now. So the timing is very important, that they send right after the packet number 2 to not allow larger ZIF timer that anybody else could go into that. So instead of sending multiple packets from the same station, here we invite the cooperative cluster to send. And then the next phase will do the same. And what you see here is a little bit smaller collision. And the reason is that we are now not allowing all the stations to collide to each other and building up the collision window. What we are doing is we are having some form of cluster heads that will try to get access. And because we have virtually less cluster heads, then that means the collision phase will be also smaller. In order to test this, we have an analytical framework for this, but we also implemented this on our open sensor platform, something that we built by ourselves. Very easy technology. It's just a microcontroller with a little bit of extensions here and an NRF 905 element. Here, this is the transmission over wireless. It's 433 megahertz. The data rate was quite low with 100 kilobit per second, but it can go 1000 meters wide. And the interesting thing is here that they are quite cheap, of course, and the medium access control does not matter with the data rate, right? We just see which medium access is better, indifferent from the medium from the data rate. But as we have a cooperative cluster, we don't only need one, we have 10 of those, where we have maybe one of the cluster heads and then 9 others are in the cluster. And then you can switch them on one by another. So if you don't want to have all 9, you can even say 1 cluster head and 4 devices in the cluster head. And from these boards, we had multiple of those. And then we did our measurements. And here you see the saturated throughput for the number of mobile devices in the system. And the black curve down here, that is the analytical CSMA-CA or the practical CSMA-CA implementation. So analytical and practical, quite good. This is the model here is from Bianchi. He made this in the 90s, end of the 90s. And this fit quite well. And then up here we have the 2 different approaches. One is packet aggregation. That is what was proposed with the analytical and the implementation, as well as also the cooperative medium access, which has a little bit lower throughput here. So question is now, what is better? Here it seems the classical packet aggregation is better. If you look at the analytical model quite nicely, you see up to 65 devices, then the cooperative Mac will be a little bit better than the packet aggregation, but this is not the real reason to go for cooperative Mac. It's more the latency. And here you see the latency for our cooperative Mac is very low compared to the blue one, which is the practical implementation of packet aggregation, and the analytical one, and also the state-of-the-art IEEE802.11 approach. You see the model and the implementation is not quite okay. The implementation seems to be a little bit faster than the analytical model. Even for the cooperative, it might be the same, but there's so little that you don't see the difference. Nevertheless, you see that the cooperative one is gaining in the latency. And this is, again, if I come back to the figure we had here, because less devices have to wait until there is a phase where they can transmit. For example, if this device has to send only one packet and it has to fight for it about all the others, and then they are using the medium so long, it's better that he gets access sometimes to spit out one small packet and that's it, right? And then the collision phase is smaller, and this is why the latency is also way better. And this explains also why we gain when there are a lot of devices, because then the collision probability increases. Okay, this brings me to the lower levels.